Hi, this is Noson Yanofsky, where the class is The Outer Limits of Reasoning. We're talking about Chapter 5. We're up to the third part of Chapter 5, and I just want to review what we did in the first two parts of Chapter 5. The first part of Chapter 5, we talked about easy problems, problems which take a short amount of time for any amount of input, essentially a short amount of time. Okay. In Part 2, we started talking about three of these hard problems. One is called the traveling salesman problem. Let's just remember, you're given a graph. Graph is a bunch of dots with edges, okay? And the graph should be complete, which means you should be able to go from any edge to any other edge. And it should be weighted, which means it has numbers on it, positive numbers. Okay? And your goal in life is to find out what's the shortest possible path that hits every single city exactly once. Okay, that's the optimization problem. The decision problem is, given a complete weighted graph, again, and given a number k, tell yes or no, decision, yes or no, can I make a cycle through every one of the cities, hit every single city exactly once, come back to the original one in within k. Okay, k miles or k distance or something like that, or k price. Okay, Hamiltonian cycle problem is a little bit easier. You're given a graph, okay, and you're asking the following question: can I make a cycle through the graph? In other words, draw a cycle through the graph which hits every single dot exactly once and comes back to the original thing. Okay, and that's a yes/no question. Okay. We also saw we can weaken this and we can say, does there exist a Hamiltonian path, not a cycle? A cycle comes back to the original one, a path doesn't necessarily come back to the original one. So we talked about that. Let's just remember what set partition was about. Set partition was, given a bunch of numbers, can I split them into two sets such that when I add up all the members in one set, it should be equal to all the members of the other set. Okay? I don't care how many each set has, I just want to know, can I do that? Okay, and we saw sometimes yes, sometimes no. Okay? All these problems take a very long amount of time. This is what's called a factorial problem. This is what's called a factorial problem. This is a 2 to the n problem. Okay, and now we're ready to begin the new stuff. Okay? The next problem is very similar to the set partition problem. It's called the SubsetSum problem. Okay, I'll show it to you in a second, but let me just tell you. And the last problem will be satisfiability. Okay, and that's about logic. Okay, so those are the five very hard problems that we will be dealing. Let me show you. Oh, let me just finish off this list. SubsetSum is also 2 to the n, very similar to this, and satisfiability is also 2 to the n. Okay, great. So let's go through some of it. Let's talk about the SubsetSum problem. First, a story. You want to go to the country. You want to take a lot of things to the country. You're going up for a week vacation. You want to take a lot of things. You have a car. Your car has a capacity. Okay. You cannot take everything. Okay. You cannot take everything, but you can take a lot. Question. Can you get a subset of all the things you want to take that's exactly the capacity of the car? Okay? Can you fill in the car with everything that you want to get? Okay, so let's just make that a more mathematical example. Let's say you're given the following numbers: 12, 5, 8, 13, 21, 16, 26, and 14. Okay, you're given a bunch of numbers, and you're given a capacity, C. Let's say C is 100. Question, can you find a subset of these numbers such that when you add them up, they're equal to 100? It's a little bit easier than the set partition problem. Can you find a subset of these numbers such that when you add them up, you get 100? You know what? I think 100 is way too big, because I think if you add up all the numbers, they'll be less than 100. Let's see, 21 and 26 is 47. 47 and 30 is 77. 77, 87, 90. Oh no, it's less than 100. Okay. Okay, so that gives me a 90. Okay, let's do, I don't know the answer to this. Let's try this. 8 and 12 is 20. 14 and 16 is 30. So 20 and 30 is 50. Can I get 50 out of the rest? And I don't know. It's 18. 24. I need 24. If I take this, it's 20. I need 24 left. 8. No. 5 and there's 18. No, that's not going to work. So let's say I take this. I take this, then I need 29. Can I get 29? Okay. Anyways, I have no idea. You can try to do it. It doesn't matter. It doesn't matter. Okay. Now, great. What's a good way of trying to do this? Well, you could try all possible subsets. Great. Let's just talk about that. How many elements do you have? 1, 2, 3, 4, 5, 6, 7, 8. You have 8 elements. Okay. How many possible subsets are there? 2 to the 8. 2 to the 8 is 256, I think. Okay, so that's not hard. You can take a computer and computer can try all possible subsets. For each subset, add up all the elements, see if it's exactly equal to 100, not less than 100. Do that. Okay, if it is, the problem is if you have n numbers with a capacity, it's going to take you 2 to the n, which is fine for small n, but if you get to 2 to the 100, I said, just like the previous one, going through all possible subsets, 2 to the 100 possible subsets will take you 401 trillion centuries to do. Okay? So that's way too hard. Way too hard. Okay, let's look for some quick tricks. Here's a quick trick. Can this be done? Well, if you add up all the numbers, you're definitely going to have less than 1,000, so the answer is definitely 0. Okay? The answer is definitely no. You cannot get up to 100. So if the sum of all the numbers is less than that, doesn't matter. You for surely can't do it. Let's do another one. The smallest number here is 5. How about if I have a capacity of 4? Well, if the smallest number here is 5, there's no way in the world you're going to get that. Okay? In fact, even if the number's 6, you're not going to get it. By the way, if the number's 40, then we do have it, right? We did this already. 40. 26 and 8. Well, anyways, I'm not very good at these things. Sometimes you can do it, sometimes you can't do it. Okay, the book has an example of one where you can do it. Usually when I teach this in front of a class of many students, there's always 2 or 3 students who are very good at these things, and they pick it up and they try to do it. I am not that good at it. Okay, that's the subset sum problem. The subset sum problem. Let's just do it. It's a decision problem. It's basically as follows. You're given a bunch of numbers. You're given a capacity. Is there a subset of the numbers that's equal to the capacity? Next. The next thing is called satisfiability. Okay? And we're going to spend the most time with this problem simply because we have to learn something that we didn't see before. Okay? And it's not in the book, so you have to really either learn it here, or you did see it in high school, or well, it's not so hard to learn. And the topic is all about logic. Okay, and you'll see later why we're doing this problem. It's a very nice problem. So before we go to logic, before we talk about it, let's talk about what logic is about. Logic is about exact reasoning. Okay, exact reasoning. It's about propositions. What's a proposition? A proposition is a statement that's true or false. True or false. Okay, so let me give you some examples of propositions that are true or false. This class is fun. That's true. This class is not fun. That's false. This class, well, let's not. I'm using black ink. That's true. I'm using red ink. That's false. Okay, statements that are true or false. 2 plus 2 is equal to 4. That's a true proposition. 2 plus 2 is equal to 5 is a false proposition. Jack is very tall. That's a little bit vague, so we don't really talk about such things. Okay, but there are, as we said when we talked about chapter 2, there are many statements that are not proposition. What's for supper tonight? That's a question, or a command. Commands are go make me supper tonight. That's a command, but it's neither true nor false. So propositions are statements about the universe that are either true or false. So they're statements about numbers, or they're statements about anything that are either true or false. So that's what we're dealing with, propositions. Okay, and it turns out with propositions you can take some propositions and you can add them and multiply them into, you can do operations with them. So let's just remember, in second grade you did this. You learned what the number 2 is, and you learned what the number 7 is, and you learned what the operation 2 plus 7 is equal to 9. Great. You also know what 2 is, and you know what 4 is, and you learned what that operation is 8. Okay? So you learned how to do this. So, guess what? With propositions, we're also going to have that. We're going to have a proposition P. I'm not interested in what P stands for at the moment. You're going to have a proposition Q. I'm not interested in what it stands for. It could stand for George Washington was President of the United States, which is a true proposition, or it could stand for it's raining outside, which could be true or could be false. But the main idea is there are operations that you can do with these to get new propositions. Just like there are operations with numbers where you can add 2 numbers and get a third number, you can multiply 2 numbers and you can get a third number, so too you can take a proposition and you can do different operations on them. For example, that's an AND, so that's AND. Okay, it's also called conjunction. Okay, that's an OR. Okay, then there's P arrow Q. I'll explain what each one of these. This is implies. Okay, and P double arrow Q. And finally, not P. I always get confused how the book does it. Okay, but we'll do that and not P. I might have it wrong. Hold on. Okay, so we look in the book. This is on page. Oh, we don't use it on page. This is on page 117. We don't use not P like that. Different classes use different things. That's not. Okay, this is called by implication. Okay, by implication means the implication goes both ways. Okay, great. Okay, I'd like to explain to you what these things mean. If P stands for I like mustard and Q stands for I like ketchup, then P and Q stands for I like mustard and I like ketchup. P or Q stands for I like mustard or ketchup. This says, if I like ketchup, then I like mustard. Okay? We'll talk about this one. This one's the hard one. We're going to spend a lot of time talking about this. This says, I like mustard if and only if I like ketchup. If I like mustard, it's the same thing as liking ketchup, one or the other. We'll see a lot more examples. And this says not. If P says I like ketchup, then not P says I do not like ketchup. Changes the proposition around. Okay? These are the operations we're going to talk about, and we're going to see how we can learn what these things, what these bigger statements are. This is what truth tables are all about. So, let's remember what we did not in second grade, like we did here, but let's remember what we did in 9th grade, or even 8th grade. Okay? In 8th grade, your teacher did something like this. X, Y, 2x plus 3y minus 5. Okay? Something like this. And basically what you did was, you plugged in different values for x and y, and you got out different values for this. Let's try it. Let's try x is 5, y is 10. Okay? What are we going to get out? Well, we plug it in. 2 times x is 10, plus 3 times y is 30. 30. 10 plus 30 is 40, minus 5, 35. Okay, so if we plug in x and y, x is equal to 5, y is equal to 10, then we get out that this final thing has value 35. If we plug in 7 and minus 5, look what we'll get. 2 times 7 is 14. 14 plus 3 times minus 5, negative 15. So 14 plus negative 15 is negative 1. Minus 5 is negative 6. Okay, let's just do one more. If I plug in 1 and 0, okay, then I'd get out 2 times 1 is 2, plus 0, minus 5. 2 minus 5 is negative 3, etc., etc. But very important, etc., etc., this list can go on forever and ever. And in fact, not only can it go on forever and ever, but you can plug in real numbers here, like 5.8632, etc., etc. There are uncountably infinite numbers that you can plug in here, and you can have your list uncountably long. You usually, as you learned in the 8th grade, what you usually do is you plug in a few values. You plug in a few values, and you get out a few things. You plug in enough that you can plot it. Great. Let me show you why logic is a lot easier than this. Okay? Because in logic, if you want to know what the value of P or Q is, well, I got to tell you what P is, and I got to tell you what Q is. Okay? But here's the thing. Logic can only be, every proposition can only be true or false. So this could be, both of them could be true. One could be true and the other one false, the other one false, the other one true, and both could be false. And that's the only possibilities. So whereas in arithmetic and 8th grade math and beginning algebra you had an infinite amount, here, because your propositions can only be true or false, one or the other, those two things. So if you have 2 propositions, you have 4 possibilities. That's it. Okay? So you can give out the full thing. The 4 possibilities are called the truth tables. So let's go through it. Let's imagine P stands for I like ketchup, Q stands for I like mustard, and P and Q is, well, we want to see how true this statement is. Well, if the statement, if I both like ketchup and I like mustard, then the statement I like ketchup and mustard is true. It is true. Okay? If I like ketchup but I don't like mustard, in other words, this statement is false, then this is false. If I don't like ketchup but I like mustard, and I say I like ketchup and mustard, well, then the statement is false. If I say I like ketchup and mustard but I like neither of them, this statement is false. Okay? Great. I now want to do for you the cheat sheet for all of logic. And once you get the cheat sheet, once you know the cheat sheet, you can do all truth tables whatsoever. Okay? It's a little bit of a cheat sheet, and it's worth doing it. Let's start with the easy operation first. How about this? Not P. What's not P? Well, this only has one variable, P. And that one variable can be one of 2 things, true or false. So, let's say the statement is, I like Betty. Okay, in class I usually talk about Betty and Veronica. But due to political correctness, we're going to talk about ketchup and mustard. But you know what, every once in a while we can, just to keep things interesting, we'll talk about Betty and Veronica. If I tell you, if P stands for I like Betty, okay, then not P stands for I do not like Betty. So if I say I do not like Betty, and in fact I like Betty, then the statement I do not like Betty is false. Okay? If I say the statement I do not like Betty, and I in fact do not like her, then the statement is true. Okay, so that deals with the not operation. Not. Okay, good. This is the AND operation. Let's do some more of these operations. P or Q. Let's see what that says. Okay, let's see. Let's say I'm saying I like Betty or Veronica. If I like Betty, and I like Veronica, then the statement, I like Betty or Veronica, is a true statement. If I say, I like Betty or Veronica, but I only like Betty, I don't like Veronica, then the statement is still true. It's as follows. If I tell you, I'm teaching this class, or I'm a billionaire, that's a true statement, because one of the things has to be true. I am teaching this class, yes I am. Or I'm a billionaire. That happens to be not true, alas, but it's still a true statement. Okay, here, this one is false, this one is true. False or true is true. If one of them is true, it's true. Okay. Finally, if I say, I like Betty or Veronica, but I like neither of them, then the statement is false. Okay, great. Two more operations. Very important. One is P arrow Q. And this is the one that people get upset about. So let's do it. Okay? We'll go through it a few different ways at a few different times. So it goes as follows. Let's say I tell you, if you drive more than 50 miles an hour, then you will get a ticket. That implies you will get a ticket. If you drive more than 50 miles an hour, then you will get a ticket. Let's go through it. If you drive more than 50 miles an hour and you got a ticket, then what I said was a true statement. Okay, great. Let's go with the following. Let's say you drive 50 miles an hour, more than 50 miles an hour, but you do not get a ticket. Okay? Then what I said was false. I said, if you drive more than 50 miles an hour, then you will get a ticket. You drove more than 50 miles an hour, but you did not get a ticket. Then what I said was a false statement. Okay, great. Now, let's say we do the following. Let's say I say, if you drive more than 50 miles an hour, you will get a ticket. You don't drive more than 50 miles an hour, but there's some corrupt cop and he gives you a ticket anyways. Well, what I said was not false. I made a prophecy. I said, if you drive more than 50 miles an hour, then you will get a ticket. You didn't even test it. You didn't drive more than 50 miles an hour. So my statement remains true. Okay? Now, most people don't like this. They think that this shouldn't have any value whatsoever. I didn't make it. You didn't try it. You didn't try to drive more than 50 miles an hour. But anyways, this is the way we're going to do it in this class. This is the way you're going to do it in every logic class you're going to take. Okay? Let's just do the last one. You ready? I tell you, if you drive more than 50 miles an hour, then you will get a ticket. You don't drive more than 50 miles an hour, and you don't get a ticket. Is my statement, my implication, false? And the answer is no. My implication is true. So, for the arrow, for the implication, the only time it's false is if the first thing, the thing in the beginning of the arrow, is true, and the second thing is false. Other than that, it's true. Okay? Great. Let's do with the by implication. This is true only when they're both true. The way it looks is as follows. This implies this, and this implies that. By implication, like bicycle, two ways, by implication. Okay, so let's go through it. If P is true, let me just give you an example. If you do well on the test, you do well on the test if and only if you study. Okay? You do well on the test if and only if you study. That means if you do well on the test, that means you must have studied. If you studied, you'll do well on the test. Now, let's say I say that, and you did well on the test and you studied, then my statement is true. But let's say you did well on the test, but you did not study, this is not true. Then my statement will be false. But I'm just telling you now, my statement is very true. Study if and only if, do well on the test if and only if you study. Okay, same thing here. You did not do well on the test, but you did study. It's not going to happen, but that's a false statement. My statement would then be false. Okay? And finally, let's say I tell you, if you study if and only if you'll do well on the test. You don't study and you don't do well on the test. My statement is not false. I'm saying the truth. You just didn't study and you didn't do well on the test. Okay. So basically, this is true when they're both the same thing. They're both true or they're both false. Okay, great. If you know this, and this, and by the way, these two are totally intuitive. Okay, this is totally intuitive, makes sense. These two, you have to look at it a few times to make sure you understand it, but it's totally okay. Great. Let's do some truth tables. Okay. Okay. I'm sorry. What you should do is you should back up and write this cheat sheet on a piece of paper. Walk around with it for 3 days straight. You'll have it down pat. Okay, great. Let's go through. Let's do a truth table. Okay. We use different letters all the time. So let's say we do this. C, arrow. A and B, arrow. Not A. Okay, let's redo this. Great. Sorry, took a little bit of my time. Okay, so I'm going to teach you how to write these truth tables. Very straightforward. You have to follow a certain pattern. Okay, pattern is not hard, whatever, but you have to do it. Let's just see. B or A and not, it's false that A implies not B. Okay? Okay, great. Okay, what are the variables here? There are two variables. We always write our variables in alphabetical order, A and B. Okay, and now we always put down truth values for these in this order. True, false, true, false. We alternate this every other one, and this we alternate every second. True, true, false, false. Okay, great. Now we're going to fill in the truth table. Okay, and we fill in the truth table as follows. We look at the statement, okay, and we ask ourselves the following question. What is the outermost operation in this statement? What is the one operation that's not in parentheses? And the answer is here. That will be our final answer, will be right over there. That will give us our final answer. Okay, but we have to build up in order to get to that. So in order to get the AND operation, we first have to look at this operation. We look at the left, we have to look at the right. Okay, great. So let's focus on this operation. The final operation here is the OR, and we're going to do the following. OR, right over here, we're going to put in right in the answer. Okay, so let's go through it. B or A. T or T is true. Okay, if one of them is true, then the other, well, then both of them are true. T or F is true. F or T is true. F or F is false. Okay, great. So that was easy. Okay, you just have to go through it. Now, notice B or A is the same thing as A or B, and I'll explain maybe what I mean by same thing later. But they're the same thing, so that's not important. So it doesn't matter. But here with the arrow, it does make a difference. So let's go through it. Great. We want to figure out what's in here. Once we figure out what's in here, we'll know the left side. Well, I'm sorry, the right side. We know already the left side. We can do that. Okay, great. How do we figure out in here? First thing you do is, as in all math, you always work from the inside the parentheses to out. So we're going to work here and here. First we're going to do not B. So let's do not B. If B is true, not B is false. If B is false, not B is true. If B is true, not B is false, true. Okay, great. Now, I'm going to do the following. We're working for the inside. So we have the answer to this thing. Now we're going to do this thing. So let's do it. Now, I'm going to write again. It's right there. I don't need to write it, and this is the last time I'll write it, but we're going to write it. So this becomes true, true, false. Whoops, too small. A little bit. True, true, false, false. Now let's do it. Let's do the arrow. Let's remember, the arrow is false only if the thing on the left is true, but the thing on the right is false. So let's do it. T arrow F is false. T arrow T is true. F arrow F is true. F arrow T is true. Great. That gives you this. This is the final operation of this statement. This arrow is the final operation. But once we finish this operation, we have to negate it. So what does it negate? It means flip this final thing. So we're going to flip this final thing. So this becomes not of F is true. Not of T is false. Not of T is false. Not of T is false. Okay? Okay. I'm sorry, I should have done this with a different thing. This arrow just shows you where the information is coming from to get that. Okay, great. Now, we got this not statement is the final operation from this side of the operation. So now we have the final thing here, we have the final thing here, and we can finally do the AND. So let's do the AND. Okay? I just want to show you where this AND is coming from. This operation, this is the final row over here, this is the final row over here, and we're going to do it together. Okay, and it goes as follows. Ready? Line by line, because that's what we're interested in. We're only sticking line by line. T and T is T. T and F is F. T and F is F. F and F, ooh, that's bad. F and F is F. That's a truth table. Okay, let's do another one. Okay, that makes sense. You can erase it. It makes sense. Okay, and that's the final truth table. Okay, so let's do another one. Okay. This closes this closes this. This closes this. Okay, this also has two variables, P and R. We're going to write them as always. We write them in alphabetical order. P, R. P, R. Okay, we put down the possible values in alphabetical order. I'm sorry, in our order. T, T, this is F, this is T, this alternates every one, this alternates every two. Okay, great. Now, just to make this more interesting, we'll put that like that. There's a double arrow. Okay, because we didn't have a double arrow last time, so now we have a double arrow. Okay, great. How are we going to solve this? We look here, this is the outermost operation, we put a box here. That's what we're aiming at. Okay, great. Now we're going to do this. Okay, in order to do this, we have to do this. In order to do this, we have to do this. So let's do not P. Not P is F, F, T, T. Okay, you have this a little bit easier than me because you have lines on your paper. If you have lines on your paper, you don't wobble around. I'm wobbling around because I don't have lines on my paper. Great. This tells us this. Now we look at R or not P. Now I can write R over here and then do the OR statement right in between them. But I don't really have to because it's here. So let's do it. R is T, not P is F. T or not F, I'm sorry, T or F is true. F or F is false. T or T is true, F or T is true. That gives you that. Great. We now have this, okay? We now have this. I like to do the AND. So again, I can write the P if I want to. I can write the P right over here, but there's really no reason for it because it's right over there. Okay, and we're going to do the AND statement. Again, just remember the AND is true only when, it's T, only when both are true. So let's do it. P and T. Notice I'm not doing this, I'm doing this. This is the final operation of this. We're doing the final operation of this and the final operation, or the final thing of this, and so we get that. So let's do it. T and T is true. T and F is false. F and T is false. F and T is false. Okay, great. Now for the final thing. So we have this is going to contribute to the final thing, and this is going to contribute, but this we already wrote over here, so there's no reason to write it again. And we're going to do it. You ready? Let's do it. T, double arrow T. Let's remember what double arrow is. If they're both the same, they give it true. Otherwise, let's get false. T, double arrow T is true. F, double arrow F is true. T, double arrow F is false. F, double arrow F is true. And that's the final answer of our problem. Okay, great. That is for two variables. Let's do another example for three variables. And I just want to tell you, I promise you, on the second test and on the final, there will be a truth table. So you have to learn truth tables. It's one of the things, the outcome assessments that we do in this class. You have to know how to do a truth table. So you got to get it. You got to get it down pat. And you'll see there's homework, there's exercises. We do everything to get you to know how to do a truth table. Okay? And it goes like this. Let's try this. Okay, nice. Notice a few things. First of all, there are three variables here, N, P, and Q. Notice also I happen to include every single operation. Or, and, single arrow, double arrow, not. Okay, so we're going to get practice doing every single operation here. This will take us a few minutes, but that's fine. We have no rush. Okay, so let's do it here with this. Now again, we're going to put down the variables in alphabetical order. We always do that. If you don't do that, you're going to get it. You're not going to get it wrong, but it's going to be hard to mark, and I'm going to mark it wrong. Okay. So let's do it. N, P, R, N, P, Q. So let's do it. N, P, and Q. Okay. Now I'm going to do something that you're not going to understand. You're not going to agree with me, but that's fine. I'm going to make a dotted line here. Okay, and I got to tell you why. I'm doing this because you have lines on your paper, and if you try to draw things, you're going to be within the lines, so you're going to be okay. But I don't have lines. I don't have lines on my paper, so I have to keep somehow lines. I have to keep somehow ordered. So that's what these blue lines are for. Again, you don't need them. I need them. Okay, so let's do it. N, P, Q. Okay. Now, we're going to put in the truth-false values. Now let's just go through this. For one variable, let's say p, p could be true or false. Very good. For two variables, p and q, p could be true or false, and q could be true or false. So you have two possibilities for this, two possibilities for this. Altogether, you have four possibilities. For three variables, you have 2, 2, and 2. Two possibilities for n, two possibilities for p, two possibilities for q. 2 times 2 times 2 is 8. And it goes as follows. You have to put in the variables as follows. True, false, true, false, true, false, true, false. Okay? Alternate that last one every one. Okay? Here you're going to alternate every second one. So this could be T, T, F, F, T, T, F, F. Okay? 2 T's, 2 F's, 2 T's, 2 F's. And finally the N, the earliest, you're going to alternate every 4. So it's going to be T, 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 F, 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 F. Okay? It's very nice. It's very nice. And now we simply have to go through it. Okay? So let's go through it. The final operation is right here. If you look, the only thing outside the parentheses is here. Okay? Great. So we're going to put that answer here. Now, I could do this side first, or I could do this side first. The final operation here will be this not. Okay? But in order to do this not, I have to do the inside. So let's first do not P. Not P is F, if P is T, F, T, T, and this is F, F, T, T. Okay? Flip it. 2 F's, 2 T's, 2 F's, 2 T's. Very good. That takes care of this. Great. Now I did this. I have this written right over here. I don't have to do it anymore. So I just have this operation. Let's just remember, by implication, it's true when they're true on both sides. So when they're the same on both sides. So let's do it. This is N, not P. So it's T double arrow F is false. T double arrow F is false. T double arrow T is true. T double arrow T is true. F double arrow F is true. Just hope I didn't make a mistake. F double arrow F is true. F double arrow T is false. F double arrow T is false. Let's just, I did that a little bit too fast, so let's just do it a little bit better. Okay. False, false, true, 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 false, false. Good. Got that right. Great. Now, I'm going to negate that. So, we got this final answer for here, for inside the parentheses. Now we negate that. Okay? And we negate it as follows. You ready? Not F is true. Not F is true. Not T is false. Not T is false. Not T is false. False, true, true. See how the lines are matching up? I'm telling you, without these blue lines, I'd be weaving all around here. Great. So that is my final answer to here. And I can tell you now, the final answer to here will contribute here. So this is going to contribute here. Let's do the right-hand side. We did the left-hand side. Let's do the right-hand side. So we call this up. We first do N and P. So let's do it. T and T is true. T and T is true. T and F is false. T and F is false. F and T is false. F and T is false. F and F is false. F and F is false. Good. Let's do Q arrow that. So we're going to watch here. Q is right here. I can rewrite it if I want, but I don't need to. Let's do it. T arrow T. Let's go through that again. T arrow T is true. F arrow. Now I'm not even looking at that. Because if you look at the cheat sheet, F arrow anything is always true. So you don't even have to look there. F arrow anything is true. T arrow, now T arrow, I have to check. T arrow F is false. It's false. F arrow anything is true. T arrow F is false. F arrow anything is true. T arrow anything is, sorry, T arrow F is false. F arrow F is true. That takes care of that. Great. Okay, now we have the final answer for this side. We have the final answer for this side. Now I do OR of it. Let's go through it. T or T is true. T or T is true. T, F or F is false. F or T is true. F or F is false. F or T is true. T or F, let's do that again. T or F is true. T or T is true. That's the final result. That is the final result. Okay, we're going to do one more just to get practice. Okay, I'm going to do one more just to get practice. Erase this. Okay, and then we'll stop doing it. But again, I promise you, I will ask you a 3-variable truth table on the third test, on the second test and on the final. So you have to know it. I will not ask you a 4-variable truth table. Why? Because that would demand 8 lines. Okay, so we don't want that. I'm sorry, that would demand 16 lines. We don't want that. Okay, so let's do another one. Okay, I make them up as I go along, but I want to have all the variables in there. That was a nice one. So let's do this. Y arrow, not Z. Or X. Double arrow. Z and X. Okay. Notice again, I just chose it that has all operations, and, or, single arrow, double arrow, not. So just we're going to get a lot of practice with all those things. Okay, that's good. And we're going to put in the variables in alphabetical order. X, Y, Z. Okay, and now most importantly, I need my dotted lines. If I don't have my dotted lines, I wander. And I tell you the truth, I've done it before. So dot 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 dot. Keeps everything very neat when you have dotted lines, as the lines on your paper show. Okay, you have it, I don't. Okay, let's put in the variables. Again, we're going to alternate on the last variable. We're going to alternate every other one. So it's going to be TF, 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 TF. Okay, this is going to be T, T, F, F, T, T, F, F. This is going to be T, 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 F, 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 F. Okay, let's do this. If we close up, we'll see that, oh, I'm sorry. Let's start over here. The last operation here is this. Okay, it's the only operation not inside the parentheses. Great. If we look at this, the only operation not in the outer parentheses is this. So first we have to do this. So let's figure out this. In order to do not Y arrow not Z, first we have to do not Z. So let's do not Z. This becomes, not Z becomes Here's z, so not of it is f t, f t, f t, f t. By the way, it might be an idea to stop the computer, try to do it on your own, and then come back and see if I got it right. Okay, let's go through this. Great, so this is the final answer for this. Now we're going to do y. So let's do it. T arrow f, T arrow f is false. T arrow t is true. F arrow anything. F arrow anything. F in the beginning, arrow anything is true. F arrow anything is true. T, this is false. This is true. This is true. This is true. Okay, great. That's the final answer for this. Now we have to do OR X. So watch what we're going to do. Hold on. Let's make sure we understand how this is going. This is the final answer for this, and we have X, so this is going to contribute to that OR, X is going to contribute to that OR, and we're going to do that, okay? So let's do it, shoot. Okay, let's do it. This is, the final answer here is F. F or T is true. T or, just watch what I'm doing. T or anything. I don't care what that X is because T or anything is true. Now let's just do it a little bit carefully. T or T is true. T or T is true. T or T is true. Great. F or F or F is false. T or second one, T or F is true. Let's do the next one. T or F is true. T or F is true. Okay. So that's our final answer for this thing. Let's do Z and X. Let's do this. I'm sorry. It's a little bit messed up over here. So let's fix it. Okay, great. Okay, let's fix it. Okay, great. Let's do Z and X. So Z and X. I couldn't write down Z, I can write down X, but they're right here, I don't have to. So let's do it. Z and X, so T and T, T and T is true. F and, I don't even have to go further, because F and anything is false. That's called lazy evaluation. Lazy evaluation means, we'll see a few examples of this, but we did see, I don't have to look at the whole thing because F and anything is false. Okay? Okay, so let's do this. T and T is true. Damn. Okay. Next. F and T is false. Let's do the next one. T and F is false. F and, doesn't matter. You see all these X's are falses, so all these are falses. Because every one of those are false, we can do it. Okay, as long as all these are falses, I don't care what they, so all the X's are falses, we got that. Great. Now, we're going to do the final operation. The final operation takes the final operation of this side, takes the final operation of this side, and brings them together. Okay, so let's do it. Ready? Final operation here is T double arrow T is true, T double arrow F is false. Let's just remember double arrow. double arrow fails when they're different. If they're the same, it's okay. T, double arrow T is true. Okay, so it's true when they're both the same, it's false when they're different. T, double arrow F is false. F, double arrow F is true. T, double arrow F is false. T, double arrow F is false. And finally, T, double arrow F is false. That's our final answer. Okay? Sounds good. Great. I'd like to just show you one thing. Hold on. In the booklet I gave you the first day, I gave you practice truth tables. And practice truth tables are very nice. Okay? Different problems. 1, 2, 3. Those are 2 variable problems. Here's 3 variable problems, different problems. Okay? And I give you all the answers to do them. I strongly recommend you do not look at this. What you do is you copy the question onto another paper, try to find the answers, and do that. Now, one thing, I have a little trouble making these little arrows. These little arrows help you with the bookkeeping, showing you how to do it. So instead of doing the arrows, what I did is as follows. I show you on the bottom what rows to do first. Okay, what columns to do first. So look, first I do this, write down the y. Then I do this, write down the x. Then I did 1 and 2, now I do 3. I do the arrow. Now I do the not. Da 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 da. Okay? And what's bold-faced here is the last thing, 8. Okay? Same thing here. Bold-face is the last one. That's the final answer. So instead of making a box around it, I make it bold-faced. Same thing here. And here you have 2, 3 variable things. Close it up, do it. Close it up, do it. Okay? It's very nice. Okay, so that is the end of truth tables. What I want to do now is talk more about truth tables and talk about the satisfiability problem. Okay. Truth tables show up all over. They show up in programming, they show up in setting up things. They show up in LSATs. If you ever, God forbid, want to become a lawyer, you have to know these things. Okay? Okay, first, you need to know 3 words. Okay? 3 words. Tautology. Okay. A tautology is a statement, a combined statement is a tautology if you have everything is true. The final answer is all true. It means no matter what variables you put in, it's true. Let me give you 2 examples of tautologies. A simple one is like this. P or not P. Okay? Let's see. That only has 1 variable, so P. P has 2 possibilities, true or false. We write that like that. Okay, let's write them up. Okay, let's put in all the things. T, F. Not P is F, T. Okay, we're going to do an OR, so that's T and T. The final answer is true. In other words, the statement P or not P is absolutely always true, no matter what P stands for. For example, I'm having green cheese for lunch today. So P or not P says, I am having green cheese for lunch today, or I'm not having green cheese for lunch today. Either way, that statement is a true statement. Today is Tuesday or today is not Tuesday. That's a true statement. Okay? Let me give you another example of a tautology. Okay? It goes as follows. This is a 2-variable one. Let me just show you what it says. It says, if P is true, and P implies Q is true, given this, we absolutely know that Q is true. Okay, let's go through this. If I tell you if you drive more than 50 miles an hour, you will get a ticket. And you drive more than 50 miles an hour, then you will definitely get a ticket. Okay? So this statement is called modus ponens. You don't have to know that, but let's just give another example. If I tell you, if it's raining, then there are clouds in the sky, and it's raining, then there's definitely clouds in the sky. Okay? Let's go through all possibilities. This could be true, 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 false, false, true, false, false. Okay? Let's go through this. We have to do this side and then this side. Q is already done. We might as well write it up already. TF, TF. Okay? And let's just do this. In order to get the answer to this, we have to first fill in what this is. So let's do this. P arrow Q is true. T arrow F is false, true, true. And P, let's write up P. This is T, T, F, F. Okay, I'm going to bring these two to do the AND, this AND. So let's do it. T and T is true, T and F is false, F and T is false, false. Okay, great. Now, final answer, final operation. I'm going to bring this together with this to get the final operation. Let's do it. T, arrow T is true. F, arrow anything is true. F, arrow anything is true. F arrow anything is true. That's a tautology. It's always true no matter what your inputs are. That's a tautology. Okay, great. So that's one word you have to know. Let me give you another word you have to know. Two, contradiction. Contradiction is kind of the opposite of, well, I don't want to use that word. Okay? Tautology means it's true. The final answer is always true. Contradiction means the final answer, hey, contradiction we talked about from the first day. The final answer is always false. No matter what, the final answer is always false. Okay? Let me give you a quick example of something like that. P is true or false. P here is true or false. Not P is false or true. The AND, T and F is false. F and T is false. Boom. It's always false. Okay? This is a contradiction. Let's go through why it's a contradiction. Because if I make the statement, today is Tuesday and today is not Tuesday, there's no way that statement is going to be true. Whether today is Tuesday or it's not Tuesday, the statement, today is Tuesday and today is not Tuesday, is not going to be true. Let me give you another example of a contradiction. Okay. I don't have to, because the first example of the practice truth tables is all F's. So that's a contradiction. By the way, the third example is all T's. So that's a tautology. And the rest are neither. Okay, great. Okay, so those are two simple things. Again, tautology, the final answer is all true. Very good. 3. The third word that you have to know is satisfiable. Okay? What I mean by satisfiable is it's not a contradiction, which means it has, let me just say, what does it mean to be a contradiction? All F's. What does it mean not to be a contradiction? It means at least one of the rows have a T in it, which means if you have some statement, okay, and you're doing the truth table of that long, complicated statement, if you have one T in the final row, in the final answer, that means there's some way, T, F, F, T, something, there's some way of satisfying this formula. Hence the word satisfiable. There's some way of making it true. Okay? All you need is one truth, and it's not a contradiction, and that one truth will make it into a good statement. So That's what satisfiable means. Okay? Okay, so on the test, I will either say to you, show it's a tautology, show it's a contradiction, show it's a satisfiable, etc., etc. Just want to show you one trick that a student did a few years ago, and I'm very careful about the way I give my test now. She did a very clever thing. I'd like to show it to you. Okay. I promise you on the second test and on the final you will get a truth table. I gave a truth table, and it was a long, complicated formula, but it's a formula basically started as follows. Not P, arrow, and then there was a lot of different things in 3 variables with a lot of different things. Okay? So I said, here was the statement. I said, show that the following tell if the following statement is satisfiable or not satisfiable. Tell if the following statement is satisfiable. It's a yes/no question. Okay? And she did as follows. P, Q, R, there were 3 variables. She went as follows. T, okay? Now, not P. If P is true, not P is false. Okay? False arrow anything. I don't care what this is. False arrow anything is true. What did I ask? I asked if this is satisfiable. Is there a true statement on your truth table? And she said, yes, there is. And she stopped. She did not do the rest of the things. Okay? That's called lazy evaluation. Okay? I just did this. That's lazy evaluation. False arrow anything is true. Stop right there. Lazy evaluation. Okay? And she got full credit for it. She had to get full credit for it because it was very nicely done. So, anyways, what I say nowadays is tell if the following is satisfiable or not. Show all work. So you can't do that trick anymore. Show all work. Okay. Here's another thing that could happen. Well, you know, if I ask you to show it's a tautology and you get me 1 F, you can stop there. But no. Anyways, when you get the truth table, you're going to have to write the entire truth table. You can't stop anywhere like that. Okay, so that's all about truth tables. Great. Now, that was a little sidebar to get into truth tables, but we're in the middle of a problem. Okay, we're in the middle of these hard problems. So let me tell you what the hard problem is. Satisfiability. Okay, this is our 5th problem, and this problem is as follows. You ready? Given a logical statement, ands, ors, single arrow, double arrows, negations, given a logical statement, tell if it is satisfiable. That's all we want to know. Tell if it's satisfiable. Okay? Great. Now, how would you do it? Well, you would do it exactly the same way we've been doing it for the past hour. What would you do? You would make a truth table. The problem is as follows. Let's say you have, let's go through it. If you have 1 variable in your logical formula, you'll have 2 rows in your truth table. Very good. If you have 2 variables in your logical formula, you will have 4 rows in your truth table. Very nice. If you have 3 rows in your truth table, in your logical formula, you will have 8 rows. 4, 16. Okay? 4 variables, 16 rows. Let's say you had 100 variables. Okay? 100 variables. Now, I'll tell you in a second, this is not a strange thing. If you have 100 variables, you will have 2 to the 100 rows. Okay? Now, how long will it take you to do that? Well, let's imagine a computer can do 1,000,000 rows in a second. Okay? Well, then to do 2 to the 100 rows will take you, you guessed it, 401 trillion centuries. 401 trillion centuries. So this problem is 2 to the n. I just want to show you where this shows up all the time. Let's say you're making seating arrangements for a wedding or something like that. Okay? So you have, I don't know, 50 people coming to the wedding. Okay? And you know that Bob doesn't want to sit next to Sally and Sally doesn't want to sit next to Jane, but if Jane is sitting with Peter, then Sally will sit with Bob only if he's next to Jane. You can write all these requirements, and if you know about seating arrangements, there's a lot of requirements. You can write all these requirements as a logical formula. And then you ask yourself the following question. Is this logical formula satisfiable or not satisfiable? Legitimate question. Is it satisfiable or not? In other words, can I somehow arrange the truths and falses of all the statements so that my final result, he's happy and he's happy and she's happy and she's happy, will work? Okay? My final result will be true. I will be able to get them to be true. So can I satisfy my guess requirements that corresponds to satisfying a formula? Can I somehow do something to satisfy a formula? Great. The only way I know how to do this, possibly, is to make a truth table. Not hard to make a truth table, but could take a very long time. Like I told you, I will only give you a formula with 3 variables because that will give you 8 rows. 4 variables just takes too much time to do. Okay, you won't be able to do it. You also make mistakes. So that is the satisfiability problem. Okay, let's just restate it. Given a logical formula, tell if that logical formula is true or false. I'm sorry, satisfiable or not satisfiable. Okay? Okay. We're going to see this is extremely important because, I'll just give you a little hint, computers follow logic. So this is going to be extremely important for later on. Okay, great. Those are the 5 problems that we have. Let's go through them again. Traveling salesman problem, Hamiltonian graph problem, set partition problem, SubsetSum, and satisfiability. All these problems take trillions and trillions of centuries to solve. Okay, I'm going to come back. I want to just clean up for a second, and we'll do some more. We're not finished section 5.2. Okay. So, question is, how much difference are these things? Let's just review. Section 5.1, we talked about a lot of easy problems, like arithmetic, searching, sorting, and Euler's cycle problem. Remember? That didn't seem so easy, but then I told you a trick with the even and odds, and that was very easy. Okay, so those were easy problems. And we called all these easy problems, we called them P. P for polynomial. Okay? Because it takes a polynomial amount of time to solve these problems. As opposed to that, the 5 problems that we saw before, 1, traveling salesman problem, 2, Hamiltonian cycle problem, 3, SubsetSum problem. No. What was that? Set partition problem. 4. SubsetSum problem. 5. Satisfiability problem. These 5 problems are much harder. Okay? These are either 2 to the n or n factorial. In other words, it takes a lot more time. When you plug in inputs of a certain size, okay, it's going to take trillions and trillions of centuries to solve these problems. Okay, now just to show you a real live difference between these problems. Okay, I just want to say, before we do this, I call such problems, and I gave you 5 examples. There are literally thousands and thousands of examples of such problems. We call them NP. Now, some people think that NP stands for non-polynomial. It does not stand for non-polynomial. It stands for something totally different. It stands for non-deterministic polynomial. It doesn't matter what it stands for. But these problems and these problems are qualitatively different. Okay, they're qualitatively different. And you can see the qualitative difference on page 118. I'm just going to point this out to you. You're going to look at it yourself. Okay, what we did was I tried a few polynomial things like log n log n squared, n to the fifth, and I plugged in a bunch of values for them. Okay, I also tried 2 to the n and n factorial. Those are 2 to the n and n factorial, just to show a contrast. Now, if you look, when you plug in large numbers here, you get out large numbers. You plug in 2,000, you're going to get out large numbers. But for the polynomials, they're okay large, but n to the fifth, if I plug in 2,000, I get 10 to the 16th. That's a large number. Okay, great, great. But for 2 to the n and n factorial, you get not large numbers, you get extremely mind-bogglingly large numbers. Okay? If you plug in, let's say, just 100, you get 9.3 times 10 to the 157. We've been working with that number. If you plug in 500, you get 1.22 times 10 to the 1,134. It has 1,000 digits in it. There's no way you can deal with these things. So these polynomials are qualitatively different than these n factorial and 2 to the n. So they're much, much harder. Now, whenever I present this stuff, I always get a few possible answers that students say, and I'd like to go through the answers. The answers are usually legitimate, and I like to go through them. So, in other words, 3 possible say, here I am saying, look, these NP problems, you will never be able to solve them. You will never be able to solve them. So, the immediate response is, yes, I will. Okay? Okay? So, one response is faster computers. Okay? Now, I'm a little bit, I don't want to tell you how old I am, but whatever. I am old enough to remember computers from 30 years ago, and I could tell you that our computers now go 10,000 times faster than computers. So you might say, look, don't tell me that this problem is going to take 10 to the 152 centuries, or 3.9 times 10 to the 4.1 times 10 to the 142 centuries. Don't tell me that, because you know what? Yes, it might take a computer now a long time to do it, but in 10 years from now, in 20 years from now, in 30 years from now, computers are going to go 10,000 times faster. And you're right. Computers will go 10,000 times faster. Not in 30 years. In 10 years from now, computers will go 10,000 times faster than they're going now. However, that will not help you. Let me show you why. Okay? Because, let me just get the number that I gave out here. Let's just look at the traveling salesman problem. The traveling salesman problem, I worked out all those big numbers for you, and I got out the traveling salesman problem takes 2.9 times 10 to the 142 centuries. Okay? 2.9 times 10 to the 142 centuries. Now, let's say you had a computer that worked 10,000 times faster than your computer now. So we said a computer now can check 1,000,000 routes in a second. Let's say your computer can do 10,000 times more routes in a second. So rather than doing 1,000,000 routes in a second, it can do 10 billion routes in a second. Okay? So let's see how much that will help you. Well, I'll tell you how much it will help you. You will be able to do this problem in 1/10,000th of what you did before. Again, if you do something twice as fast, you can do it, you get it twice as fast. You can do it in 1/2 of the amount of time. Okay? If you do something 10 times faster, you can do it in 1/10. So I'm telling you, if you have a computer that works 10,000 times faster, okay, what that will help you is you will be able to do the problem in 1/10,000th of a time. So if this takes 2.9 times 10 to the 142 centuries, then if you divide by 10,000, you will do the traveling salesman problem for 100 cities, n is equal to 100, at this amount of time. Let me tell you what this amount of time is. It's 2.9 times 10 to the 138 centuries. That's what this divided by 10,000 is. It's that. You just chop off 4 zeros. Dividing by 10,000, chop off 4 zeros, you get 10 to the 138 centuries. Now, 10 to the 138 centuries versus 10 to the 142 centuries doesn't make a difference. Not going to help you too much. Not going to help you too much. Okay? It's just not going to make your life much better. That is a immensely long amount of time. That is also an immensely long amount of time. That's not going to help you much. Okay, so faster computers are not really going to help you. Let me tell you something else that most people think will help them. Okay, and that is as follows: multiprocessors. Okay, computers nowadays are very good into splitting up the problem. Take the problem, put it up on the cloud, have everyone download part of it, and work out the problem. So let's say you're doing the traveling salesman problem for 100 cities. Go on YouTube, Facebook, whatever, get 10,000 of your friends to download the problem. Let's say you're doing this in 20 years from now, 10 years from now, when computers are running 10,000 times faster, you have 10,000 different people working on this, or 10,000 different computers working on this same problem at the same time. Now, if you have 2 processors, 2 computers working at the same problem at the same time, you might be able to split the problem into half the time. Okay? If you had 10 processors, you can do the whole problem in 1/10 of the amount of time. How about if you had 10,000 processors working on this fast thing? So 2.9 times 10 to the 138 centuries, and you do it with 10,000 processors. How much will that help you? Well, it will help you. It will help you because that will give you 2.9 times 10 to the 134 centuries. Okay, 2.9 times 10 to the 134 centuries. Now, that's still an immense amount of time. I want to explain to you why this number was so humongous. This number was so humongous is because basically you did 100 possibilities for the first city times 99 possibilities for the second city times 98 possibilities for the third city times 97 possibilities for the fourth, etc., down to 3 times 2 times 1. That's what factorial is about. But if you think about it, what are you doing? You're adding 2 digits to your problem. You're taking 100, which is a 3-digit number, you're adding 2 digits to it. 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 Till you get to 50, where you're pretty much, most of the time, you're adding 2 digits to each time. This problem is an immense problem. Faster computers, multiprocessors, are not going to help you. Okay, great. Another thing that students always say, oh, don't worry about it, we'll get this problem solved, okay, is quantum computers. Okay, well, let me tell you a little about quantum computers. There's a book I wrote on quantum computers. It's a nice selling textbook. It's from Cambridge University Press. They published this book, so I know something about quantum computers. In fact, it's selling very well, more than most other books, and has more positive reviews on Amazon and Prime than any other textbook in quantum computers. Let me just tell you a 2-minute introduction of what quantum computers are all about. Quantum computers are about computers that use strange things in physics. And one of those strange things is quantum mechanics. And in quantum mechanics, you can do a lot of very strange things. For example, one particle can be in more than one place at one time. One thing can be in more than one place at one time. Now, that's very strange. It's counterintuitive. You don't believe it, but it happens to be that it's true. Let me just say, so people are trying to get quantum computers to do amazing things like that. For example, if I'm searching for an object, Okay, we talked about searching before. Let's say you're given a bunch of things and you want to search for it. You say, okay, let me try that one. 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 That's the way a computer works. With a quantum computer, you might be able to go and break up into many different pieces at the same time. I told you one particle can be in more than one place at one time, and try all possibilities at the same time. Okay, that's what a quantum computer can do. Okay, it's a little bit more complicated than that, but pretty much that's it. Although, buy this book. It will make you happy. It's a very good book. Okay, so let me tell you, I know something about quantum computers, and you might say to yourself, look, I'm going to get faster computers, and quantum computers are much faster. I'm going to get many computers, all of those faster, many computers are all going to be quantum computers. So it's going to turn out that I can do it in 2.9 times 10 to the 130, the square root of 2.9 times 10 to the 134 centuries, which is pretty good. This is equal to about, let's say about, 2.9 times 10 to the 70, no, 134 is 62, 66. What's 134 divided by 2? That's 60, 67 centuries. So, if you did it all with quantum computers, then yes, it would square root the amount of time. Square rooting the amount of time is 2.9 times 10 to the 67 centuries. Still beyond belief, beyond the ability of man to know, of the human race to know it. You will die, the sun will go out, extinguish before you know the answer to this question. And notice, the question is not a hard question. I asked for 100 cities. How about if I wanted to visit 200 cities or 300 cities? I want to visit the 300 most populous cities. I'm a traveling salesman. I want to do it. The numbers would be astronomically larger than these numbers. And it's a legitimate question. It's a simple question. Okay? But the way to, what we've said so far is that these problems seem to be inherently unanswerable. You cannot answer them. Not even with faster computers, not with multiprocessors, not with quantum computers. It seems you cannot answer them. Okay? There's one other answer that people usually give me. And that is better algorithms. They say, look, going through all possible routes, that's a stupid thing. You can't do it, right? But maybe there's a better trick for solving the traveling salesman problem. Maybe there's a better trick for solving the Hamiltonian cycle problem. Remember I taught you that better trick of solving the Euler cycle problem? Maybe there's a better trick for solving the Hamiltonian cycle problem. Maybe. Why not? Okay? The trick I taught you about evens and odds to solve the Euler cycle problem, that you didn't think of beforehand. It's a very clever trick, and it works, and it gives you a polynomial algorithm to solve it. That's very, very nice. You didn't think of it beforehand. You tried to go through all possibilities. There was a trick. Maybe there's a trick to solve these problems. Okay? Maybe there's some quick way of doing them. Okay? The answer is, maybe there is. I don't know of any better way. And for a long time, people have been looking at it. But what we're going to do in section 5.3 in the next class is talk about that and see maybe there is a better algorithm, maybe there's not. And we're going to come to the conclusion, well, I don't want to tell you what the conclusion we're going to come to, but that's going to be dealt with there. So again, these faster computers, multiprocessors, quantum computers, they're not really going to help you that much solving the problem. Better algorithms, yes, that will help you, if you can find them, if they exist. We don't know if they exist yet. Okay? And we'll talk about that more next class. Thank you. Have a good day.